Hello, everyone, and welcome to the November meeting of the Howard Astronomical League, also known as HAL, H-A-L. And I'm thrilled to have everybody here today. We have a great meeting all lined up for you. And so let's just jump right in. As soon as I click on the right screen, we'll jump right in. Here we go. As always, we'll start out with a little astro humor. See all of you laughing very hard. I'll wait till you stop so we can continue on. Remember, I'm always looking for astro humor. After doing this for 3 years, you know, it gets a little tougher to find some good ones. So I appreciate them when you email them over to me. So I'd like to welcome everybody officially here, our regular members. And I also want to welcome any new members and any guests if we have anybody today. So are there any new members on? Just mute yourself and say hello. Any first timers? Any guests today? Wow, just the regular gang. That's a first. Well, welcome, regular gang. So we
actually, no, I have a student here.
Okay, well,
one of my students is here, but he said he doesn't have a camera because he's on a computer with a camera.
So
I don't know if he's going to say hi on the chat, but I have a student here tonight.
Okay. Well, what's your student's first name?
Dawn.
Dawn, welcome, Dawn. We're happy.
Sean, S-H-A-W-N.
Happy to have you too, Sean. All right, as always, I want to take a moment to thank all of our board of directors members and our committee chairs. You know, without all of you, we wouldn't be as successful and we wouldn't be able to do all the programming and everything else that we do. So thank you very, very much, which is a good lead into it's getting to that time again. Or in January, we hold our election for the 2023 Board of Directors for HAL. And so nominations are open. So let me turn this over to Mr. Johnson. Jim is our election committee chairperson once again, and we really appreciate doing this because it's kind of a big job. So Jim, unmute yourself and it's all yours.
Yeah, thanks, Phil. Yeah, the time coming up for the elections again. The elections are held on at the January HAL meeting, regular January HAL meeting, January 19th, 2003. All HAL members are eligible to run for office, even though some of the present board members might run for their same or a different board seat. All seats are considered open and everybody should consider running for office. If you're interested in just talking about it, either myself or any of the board members would be glad to talk to you about it. If you would like to nominate yourself or someone else for a board position, election@howardastro.org is the official HAL email address. So send an email to either ask questions or make nominations. And the deadline for nominations is 24 hours before the January 19th meeting. So 7 p.m. on January 18th is the deadline for nominations. That's it. Thanks, Phil.
Thank you. Anybody have any questions for Jim? Nope. Once again, thank you very much for Jim for being the committee chairperson again for the elections.
You're welcome.
Well, we're down to our last event, our last public, or that's not public, the members only star party, our last published star party for the season. So that's this coming Saturday. Chris Miskowitz is the host, and the weather, I understand, is looking okay, so that'll be great. And so the party will start at sundown, which is getting earlier and earlier, and we'll go till the host is done. So I'm looking forward to seeing people out there. I'll be out there a little bit late myself. I have an event I have to go to first, and then I'll come on out over at Alpha Ridge. So moving on. For those, I think everybody here, almost everybody here in the meeting tonight knows about our Discord group. And every month, the Discord group has a contest amongst themselves where they pick a single target. They observe an image of that target, and then they take their image and process it, and they vote amongst themselves on who did the best, who got the best picture for that particular month. So we're always 1 month behind because the November is still underway. And the congratulations to Brad Martin for this picture of the Wizard Nebula. It's beautiful. Brad, are you on? All right, he'll have to watch it on YouTube. So anyway, does anybody know what the November target is? I didn't look.
Yeah, it's the constellation Cassiopeia.
Oh, wow.
You can do wide field, you can do something up close, whatever floats your boat.
Very good. So we'll look forward to seeing that. And once again, like just about everything else that goes on here at the club, you can always see what's happening right through our website. And actually, the Discord group is always kind of right up front there on the main page. There's a click on that, and you can see what's happening. And also, if you want to get involved, that's the way. So a big congratulations to our own Jim Johnson, who you've already heard from once today. Jim, his picture was selected by TeleVue's blog for the Eclipse the other day. And Jim, you want to talk about this a little bit?
Yeah, I was imaging the eclipse. I think I was taking an image about once every minute from the time that it started all the way through to the beginning of totality. And once it got to totality, I started clicking off 100 frames to stack and compose this image. And I only got 97 of them before the moon was in the trees on the western horizon. So that's a stack of 97 frames with a Canon EOS 60DA. And the way TeleVue found me was I mentioned that I used the TeleVue NP10 IS and the 2X PowerMate.
Fantastic. Boy, just think if you would have got 3 more in there, how good it would have been. Made it 100. Congratulations. Any questions for Jim?
Yeah, what do you mean by TeleVue found you? You posted them someplace and they were surfing and came across them?
I post my images on Flickr and TeleVue. If I mention in the description that I use TeleVue equipment, they usually fave the image if they like it. And this one, they asked for permission to include it in the blog.
Okay. Thank you.
Yeah.
Anybody else?
Congratulations, Jim. That really is cool.
Thanks.
All righty. And we have some congratulations to the Artemis team for having a very successful launch, and the mission's on target still. And hopefully will continue to be. So congratulations to all of them. And some of you I know were out there and watching the launch, and the rest of us were either sleeping or watching it on TV, or watching it on TV sleeping.
Especially the red team that fixed the leak.
There you go, right. And then I'm going to start highlighting a particular image from James Webb, because it's just unbelievable what keeps coming back. And many of you probably have seen this. This was one of the most recent ones that they published, which is, you can see the description there on the bottom of this protostar and everything's going on, but it's just spectacular. So I'm looking forward to having somebody from Space Telescope Science Institute talk to us about James Webb, and like we've had in the past for Hubble. So it's really, really cool. And then tonight is this peak of the Leonid meteor shower. Here it's going to be a little bit iffy on the weather, which is no surprise because anytime there's a astronomical event that we get clouds. And as you guys have heard me say before, that somebody once told me that an astronomical event is Maryland's solution to the drought. So, but anyways, but it's not just tonight, it'll be going on. So hopefully we'll be able to see some meteors over the rest of this month.
Bill,
Yes.
it's actually predicted that Saturday morning at 1 a.m., sorry, there will be a peak of this shower due to crossing
Bless you.
due to crossing a stream from 2 centuries ago or so that could be pretty good. They're saying maybe more than 200 meters an hour.
Whoa. All right. That's great information. So I guess I'll dress my warm clothes for Saturday.
And they expect it to be a short peak.
Yeah.
In the article I read.
Now, Gene, are you talking Friday night into Saturday or Saturday night into Sunday?
Yeah. Friday night into Saturday morning.
Okay.
1 a.m.
All
Well,
right.
somewhere between 1:30, somewhere in there.
Well, if there's a key holder that wants to open up one of the parks, just send out an email and let everybody know. I won't be able to do that tomorrow night, but so very good. So what we're going to do, as I said, we're going to move some of the other business to right after our guest presenter, and we'll cover it that way this week, and then we'll get into our pictures. But there's one more thing I want to show. So this comes from nobody from our group here, but Dave Zolette showed me this on Instagram, and it's just so cool. So this is called Devil's Horns, and it was a partial eclipse of the sun as the sun was rising. And this was captured in Qatar, and it's just a little bit eerie and very, very cool. So just to have the moon and the sunrise exactly at that point at that time. Yeah, great monster movie. So now what I'd like to do is I'm going to turn it over to Joel. And then after Joel's introduction, I'll stop sharing my screen. And then Lori, you could share yours. Go ahead, Joel.
Thanks, Phil. Have the pleasure of introducing Dr. Lori Figge. I believe I was trying to recall, I think I met Dr. Figge about 15 years ago as a group around Maryland and Washington area were preparing for the 2009 International Year of Astronomy. And Dr. Figge had finished her post-doc work. And so you can read her bio. It was on the HAL website. There's a link to that. So I won't go through that in her introduction. But what I did want to share is the picture here to the left. Sorry, Lori, I found that picture from your Astrocast in International Year of Astronomy as a solar system ambassador. But the picture on the right is really epitomizes what I admire about Dr. Figge is, and reading even the last line of her bio. From an early age, Dr. Figge received encouragement and support from her family to pursue a career in astronomy and enjoys sharing her own science, promoting science literacy, and inspiring others to enter the STEM fields. And I think besides our enjoyment of viewing the night sky when we have our public star parties, we all get such a kick out of paying it forward to the next generation. And on the right-hand side, in 2009, Dr. Figge came to the Celestial Searchers, which was out at Bushy Park Elementary, where she was an honored graduate a number of years ago, and then graduated high school in Howard County at Glenelg. But she came and did the Build a Comet exercise that I had been doing for about 10 years, but not until Dr. Figge did it actually look like a comet. And when she showed films of whatever, I don't know if it was the epoxy mission or the Rosetta mission, and she showed photos of the comet, it looked just like what was sizzling in front of the kids. So it was very exciting, and thank you for the tips on how to make comets. And in that, I turn it over to you, Dr. Figge.
Great, thank you for the invitation, and I'm glad to be back here many years later to the group of Howard County astronomers. Let me go ahead and share my screen now. Okay, so I'm going to jump right in. Clearly, if you read my bio, cometary science is my hot topic. I dabble in lunar hydration and asteroids a little bit. I was very excited to watch the DART experiment from my own home, but I was not in mission control or anything like I have been for some of the comet missions. And I've studied Io and Jupiter's moons, and the water on Europa and Enceladus all excite me, but comets are really where my heart is and where my expertise is. And I'm a spectroscopist at heart, so really what I look for in most of the things that I study and analyze is the composition and understanding that composition and sort of the origins of that body and how it relates to the origins of Earth or the origins of the solar system. So I'm going to jump right in here, and my talk, Cometary DUIs Detected Under the Influence, because comets are very small, very dark bodies, and they're very difficult to detect unless they have a big, bright, fuzzy coma, which is all the material that's come off of the comet nucleus when they come much closer to the sun. So I'm going to talk to you about comets, and one of the comets that are sort of a hot topic right now toward the end of the talk, which is a target of James Webb. Unfortunately, those observations, I'm not part of those observations, and the observations are not public yet, so I don't have results specifically from James Webb, but I will be getting into that comet a little bit. So to start off, we explore the solar system to understand several things. It's not just the joy of discovery and the exhilarating part of exploration, but we really, as humans, we've got that human nature. We want to know where we came from. We want to know where we're going, how is the Earth evolving? How did Mars evolve to what it is? How did Venus evolve to what it is compared to Earth? And are we alone? Is there life out there? Is there intelligent life out there? All of these types of questions really get to the heart of why we explore not just the solar system, but also the universe. So why comets? If the universe is so vast and the planets have, several tens of satellites around them, and some of them might be harboring, saltwater oceans, why are comets interesting or important to study? So first of all, they're just beautiful, right? Their interaction with the sun is beautiful. Humans can witness it. As you brought up, tonight is a meteor shower from a comet tail crossing. So comets interact with the Earth. They're beautiful. Humans can witness them and have been witnessing them for centuries, millennia, really. They can also be dangerous, along with asteroids. Comets can still impact the Earth. They have Earth crossing orbits occasionally, and that impact could cause a mass extinction and could be hazardous to life on Earth. As we know right now, Earth has about 200 craters ranging in various sizes and location around the Earth. There's probably more in the ocean. We just don't know about all of those. So things have impacted the Earth over the history of the Earth. Comets are old and wise. And what do I mean by that? I mean, they are some of the oldest bodies in the solar system. They keep a record of formation of the solar system, the conditions when the protoplanetary disk was forming, the material that was there, the ices that were there, the volatiles that were there that formed the rest of the planet. So as the rest of the planets evolved and accreted and got much larger, and the heavier metals and such went to the interior of the planet, you have a lot more processing going on those planetary bodies, and you might not very easily be able to deduce or infer backwards what were the original ingredients. Whereas comets are very sort of loose aggregated bodies. They don't have a lot of evolution. Typically, I'll show the ones that do. And so they really record that information. They're also stored out in the furthest part of our solar system, where those ices remain ice. The volatiles remain with the comet until they come close to the sun. And so it really does preserve that sort of beginning record of our solar system. And what are comets made of? Like I mentioned already, the dust, the ices, the organics that are making up the rest of the solar system around us. So comets tell us where we came from, forming 4.5 billion years ago, where they condensed far from the sun. And here's just an image to get you thinking about a protoplanetary disk spinning and all the material accreting. Comets, we see a lot of mixing in the material of comets. We thought there were two very distinct reservoirs, the Oort cloud comets, which I'll talk about in a minute, and the Jupiter family comets, but we're seeing it with their compositional studies as they progress and get more sophisticated, that there is actually sort of a blurry line between the two populations, and comets might not have formed in two very discrete locations, and there might have been a whole lot more mixing within that protoplanetary disk than originally thought. So what is the Oort cloud? The Oort cloud is this, we'll call it spherical, this large region outside of the disk of the solar system, mostly spherical, where as the giant planets were forming and migrating in the planetary ecliptic plane, essentially, all of the other material that was in that disk got scattered. And some of it got scattered into the Oort cloud, some of it got scattered out to the Kuiper belt and the trans-Neptunian region, and some of them got scattered in closer to the sun and actually went into the sun under the gravitational attraction. So the Oort cloud still stores many millions of comets, we believe. We don't have an exact count because we can't observe the Oort cloud directly, but what we can observe are comets as they come in from the Oort cloud. So every once in a while, there is a passing star that actually perturbs gravitationally these comets that are in the Oort cloud, and one of them comes into the sun, comes past Jupiter to the sun, and heads back out. And depending on the shape of its orbit, whether it was put onto a hyperbolic orbit or not, it might leave the solar system completely, or it might return to the Oort cloud, never to come back into the solar system or into the inner solar system, or it might actually stay a little bit more local and return on a periodic orbit that could be thousands to millions of years old. And as I mentioned, we also have the Kuiper belt objects and trans-Neptunian objects, which house several comets that we believe get kicked in to become Jupiter family comets. That's sort of the transition period, transitional area. Once an Oort cloud comet comes in and gets sort of stuck in the inner solar system compared to the larger extent of the Oort cloud. If they're in the trans-Neptunian orbit, they could be perturbed by Jupiter much easier and then become a Jupiter family comet. Okay, so I sort of hinted on these different orbits of comets when they're in the Oort cloud, but what about the ones that are a little bit closer, the ones that we really interact with and can see from the Earth? And those include the short period comets, or the Jupiter family comets, which come around every 5 years or so orbiting the sun. As I said, they come from the Kuiper belt. And they go out to about Jupiter's distance and come back in close to the sun, and that's why their period is every 5 years or so. We have the HAL type orbit, or HAL type comets, which orbit somewhere, I mean, this is not a hard boundary, but somewhere between 50 to 100 years or so. And HAL, by the way, is coming back in 2061. So put that on your calendars if you haven't already. But they orbit between Pluto and the sun, or generally that distance. And that's why their orbital period is in the 100-year range. And then we have those long period comets, which, if they're periodic, they do come from the Oort cloud originally, but they stay a little bit closer than the Oort cloud, and they do interact with the sun. They do shed some material. They have some mass loss. Then you've got the Oort cloud comets. They stay out there until a passing star might perturb them in some way. Okay, so we see, if you think, what does a comet look like? You're probably, thinking of what you could see with the naked eye, which is this long, beautiful tail, the fuzzy ball, or something like Comet Holmes several years ago that had the outburst, and it just grew in size as that outbursting shell of material became a naked eye object in the night sky. But really what a comet is, it's a couple kilometers, maybe 20, 30 kilometers for the largest comets that we know of, nucleus made of rock and ice, carbonaceous material and ices, water ice, carbon dioxide, carbon monoxide, some methane, that kind of thing, and some organics. And the organics are both solids and gaseous and ice. And that makes up the solid nucleus itself. The solid nucleus is as dark as charcoal. So even though there's some icy material in it, and on the surface, it's not a shiny diamond in the sky. It is very, very dark. Then as soon as a comet comes in and gets activated by the sun, feels that sun's warmth, the material, especially the ices, start activating the material shedding process. And so that's what starts forming the tails. Both the ion tail and the dust tail are formed because of this material coming off of that solid nucleus, usually pushed off of the nucleus from some gas that's either on the surface attached to dust particles and they lift together, or the gas is subsurface and it sort of drags out material with it, or lifts surface material as it escapes the nucleus. So that's the anatomy of a comet. You've got the solid surface called the nucleus, but then around it you're surrounded sort of by an atmosphere that is somewhat gravitationally bound to the comet, and then the tails, which no longer are under the influence of the comet but follow in its orbit. The ion tail is usually straight and narrow, pointing opposite of the sun because of the charged particles and the solar wind interaction, and the dust tail usually is curved and sometimes has some striations and such in it that you can see with the telescope or with the naked eye. And that's because once the dust is released, it stays in the relative orbit of the comet, which is a curved ellipse. And so you get the curvature seen from the dust tail. Okay, so I'm going to talk about several different comets here. Some of them, hopefully many of them you've heard of in some way, shape, or form. Comet Halley is probably the most observed comet. Is the first periodic comet to be predicted to return. It was discovered, and there's a little bit of historical debate whether it was discovered in 467 BC or 240 BC, but 240 is a definite date, but there is a comet that works out to be two or three orbits prior that is in some notations, and so it's possible that they were referring to Comet Halley in 467 BC. The Comet Halley is responsible for the annual Orionid meteor shower, which is in October, and not in 1995, but in 1985 and 86, there was a huge observing campaign to observe Comet Halley, and it included flyby missions. Unfortunately, none of the flyby missions were NASA participation. The European Space Agency and the Soviet Union had missions that flew by Halley. So Halley was the first comet that we actually have some images of, some compositional data of from an actual flyby. All the rest have been ground-based observations prior to that. And from the flyby, we could actually deduce and measure the nucleus. And so, we could finally see through that shrouded coma to see the nucleus. And the nucleus size was about 9 by 4 by 4 miles. It was oblong. It was not a circle. It was not a spherical cow, as physicists like to simplify things. And this comet had surface material coming off in jets that you could see without stretching the images, and that sort of advanced our study and understanding of comets at that point in time. So as I mentioned, we've been to Comet Halley as a spacecraft target, and here it is on the left. All of these are to relative scale size. And so you can see there's a variety of shapes, a variety of sizes, with Comet Hartley 2 over here in the top right being the smallest comet that we've flown by, and Comet Halley being the largest. Now, a Jupiter family comet is the only comet we have gone to with a spacecraft, and there's a very specific reason for that. Many specific reasons for that. One is that they're periodic, they're predictable, so we can study them for multiple decades, multiple apparitions around the sun before we send a spacecraft to it, so we can reduce the risk of our spacecraft. We kind of know what we're getting into, even if we don't know specifically what the nucleus looks like. And sometimes comets can be a little bit unpredictable with fragmenting or outbursting. So we might not be able to predict the activity perfectly, but we can have an idea if we've been studying the comet for a while before we send a spacecraft there. The other thing is Jupiter family comets, by their nature of their orbit, come much closer to the Earth than any other type of comet in their orbit. And so we have a chance every 5 years to get to a Jupiter family comet that might be crossing or somewhat close to the Earth's general environment, and we can much more easily get a spacecraft there with less fuel, less delta V, and all the things that are required to get a spacecraft to something. And several of them are in the ecliptic plane, again, easier to get to just by the sheer transfer orbits that you need for the spacecraft to get there and to fly by them or to orbit them. So the Stardust mission flew past Comet Wilt 2 in 2004, followed, I'm sorry, we should start with probably Borrelly. Down here, Borrelly, this sideways bowling pin in this picture, was flown by in 2001 by the Deep Space spacecraft, which was a technology demonstration for NASA and really only had one camera and a few other instruments, but was not well equipped to be doing a cometary study. It was more a technology demonstration. Then Stardust flew by Wilt 2, which if you only had these two comets and Comet Halley, they are very different. Wilt 2 has a whole bunch of pits. It's much flattened compared to Borrelly, which looks like this bowling pin. And then 1 year later, when we flew by Tempel 1, we saw some smooth flows on it. We saw something that looked more of more like an actual impact crater rather than pitted regions. There's ridges and terraces. And then the extended deep impact mission, or the epoxy mission, went past Hartley 2 in 2010, and we saw an extremely small version of a Borrelly looking comet. It had that bowling pin shape with a very smooth waist, but it was actively spewing material, which I'll show in a few minutes. And then we just finished up a few years ago the Rosetta mission, the European and NASA combined mission to Comet 67P Churyumov-Gerasimenko. And that comet kind of looks like an apple core that you bit into, or a rubber ducky when you sit it the other direction. And so again, very huge diversity in all of these comets, in their shape, in their activity, in their size. And so even though these are all the Jupiter family comets, they should maybe be similar. They're coming from a similar region as once thought. These things are very, very diverse, and we've learned a lot from each of the ones that we've been able to study. Including things like, where is the activity coming from and how icy are these things, right? We used to think of a comet, or used to call a comet a dirty snowball. And it's becoming more and more obvious that maybe these are snowy dirt balls instead. They have more carbonaceous and organic material and a little bit less volatiles, at least on their surface. They might have deep reservoirs of volatiles, but all of the comets we've been to up close that had the ability to detect water ice on the surface, which either means using a spectrometer to actually study the signature and fingerprint of water ice, or having enough cameras with filters that you can get some sort of relative color images, where you can see sort of bluer material is generally icier material, and the redder material is more the carbonaceous material. And so here's an example of Comet Tempel 1 that we went to with deep impact, showing both the slope of the material in one of the icy patches up here on the comet, and how it's got a blue slope. So the blue slope shows higher reflectivity in the short wavelengths and less reflectivity in the red wavelengths or the longer wavelengths, but we also had spectral coverage, and this is a telltale absorption of water ice. So we know we definitively detected water ice on the surface, but when we did the measurements, it was really only in very small places, which if you do the calculation, it's only 0.5% of the entire surface had water ice on it. Similar things were found at 67P Churyumov-Gerasimenko, where the Rosetta mission and spacecraft spent 2 whole years there. They saw a full season coming inbound to the sun and outbound again, and there was very little ice actually on the surface. In fact, it was very small patches even at that. It's not like a full ice skating rink here. It's just little mounds of ice. And generally it was very close to a shadowed region. So the ice does not stay very long on the surface. The surface of comets are not covered with ice. So basically what's happening at something like Temple 1 or CG is we think, there's this very small amount of ice on the surface, and it's water ice because the other ices should not be able to survive very long on the surface. The temperatures are just too warm. They will sublimate much sooner. And they, when they're feeling the sun's warmth, they evaporate, but they don't actually evaporate. They don't go through the water phase. They go straight from the ice phase to the gas phase in a process called sublimation. And so it can take some dust with it, but it's really a surface process, and it's a very small surface process. And here's a water map that I actually made from the deep impact data, and the sun is to the right in this image. And what it's showing is on the nighttime side, there's really not much activity, but on the daytime side, where it's actually feeling the heat of the sun, this is the subsolar point, that's where you're getting this sublimation. So this is a surface process or a very near surface process. There's not a lot going on deeper than that, but you still only need a few small ice patches to get this material in the coma. Opposite to that, however, when we got to Comet Hartley 2, we basically encountered a snowstorm with the epoxy deep impact spacecraft. So you can see in this image, this is not stretched or, there's no special image processing here. This was one of the images we got directly from the spacecraft. And you're looking at all of these little white dots in the picture here, in the image. They are not cosmic rays. They are actually pieces of icy dust that have come up off of the comet from areas like this, where you see these little jets being activated. And so many of these little jets were actually being activated on the night side. So we know that they are not water activation. They are something else that's coming from deeper within the nucleus and throwing out all of these other icy particles. So when we studied it further, the icy particles that were in the coma were water ice, but the gas that's dragging them out from the deeper interior of the nucleus is actually carbon dioxide. And so the process on Hartley 2 is a little bit different than that process that we saw on CG and on Temple 1, where in fact there's deeper reservoirs of material where carbon dioxide ice and water ice are mixed, or carbon dioxide might be even deeper. And as it turns to gas, sublimates and goes through the layers of the comet reaching the surface, it starts dragging other ice particles that are less volatile with it, as well as dust, and comes out into the coma of the comet. And so that's what we saw at Hartley 2. So an active process like that, where you're actually dragging material from inside of the comet to the outside, accounts for large active areas of comets. So Hartley 2, before we got there, was mathematically considered to be 100% active. And all that means is they measured the amount of water that they could see in the coma. They had an estimate of the size of the comet. They knew it was fairly small, but they didn't know exactly how small. They didn't know exactly the shape. And they said, okay, with that amount of water that's being produced per second, which is the measurement you can make from the ground, and the size estimate that we have of the comet, it has to be 100% active across the surface. Like every part of the surface needs to be spewing out this material to get that production rate of water in the coma. However, when we got there, we saw what was actually accounting for all of that material. And in fact, it was because you have lots of ice particles being dragged out by that CO2 that you get extra material in the coma that had nothing to do with the surface. But once it's in the coma and feels the light of the day, literally feels the sun's warmth, it sublimes and you have more water than you needed to account for the surface. So we assume that the active, very highly active comets that we have by measurements of their water production rate, even if we've never flown by them with a spacecraft, that they have a similar process going on, thanks to our study of Comet Hartley 2. Now, I point out this one thing right here in the image I'm showing this in this diagram, that some of the material, both ice and dust that were drug out here by the CO2 jet, falls back on the comet. And we saw that in Hartley 2, not actively happening. We didn't see a piece actually fall back onto the comet, but we saw the trajectories of some of the ice and kind of knew where they were headed. But we also just saw this very smooth region around that neck portion of Comet Hartley 2. The reason why we didn't see any of the particles actually fall back onto Hartley 2 is because the flyby was so fast. It was 10 meters per second. Or, I'm sorry, 10 kilometers per second, as we flew past, that we only had Comet Hartley 2 in focus and greater than 1 pixel, so resolved, for 2 hours prior to closest approach and 2 hours post closest approach. So this material took more than 4 hours to fall back. So we didn't actually see the material falling back from our jet. But anyway, this process is going on at Hartley 2, and it helped to explain some of the things that we saw when we first arrived at 67P before we had done, a large study of it. We got there and we saw a lot of very smooth areas that looked like maybe pits that were filled in and such on the northern hemisphere of CG. And what was happening is actually the southern hemisphere of CG, because of its obliquity, which is the tilt of its axis as it goes around the sun. The southern hemisphere actually sees the sun during perihelion. The northern hemisphere, and perihelion, for those who don't know, is when the comet is closest to the sun. And the northern hemisphere tilts toward the sun and sees the light of the sun and the warmth of the sun when it's at aphelion, when it's furthest away from the sun. So the north does not have a very warm summer. And hasn't even, a pretty cold winter because it's in shadow, even though it's close to the sun. Whereas the southern hemisphere feels a very large seasonal effect and a lot of heat during its summer. And so what's happening is the south is producing a lot of material, having these jets and everything during the summertime, and that material gets lofted just like it did on Hartley 2. And where is it going to fall back? It doesn't have the neck that's necessarily falling back for CG, but it's falling back on the northern hemisphere, which does not see the sun during the summer months. So down here, you can see how smooth some of those regions really are. All of this is material that has fallen back. And most of that material is devolatilized, which means that all of the things that were ices have evaporated, right? They sublimated, and they are now in the coma of CG. But the dust and a little bit of water ice has fallen back on the surface.
Hey, Lori?
And yes.
Excuse me. Ken has a question. He asks in chat, is there a direct correlation between the age of a comet and its distance from the sun?
That's a good question. And no, there is not. The Jupiter family comets are closest to the sun at the moment in their orbit. And so they are getting, each time they go around the sun, they lose mass and they will eventually disintegrate or just not have any more material to sublimate and become dormant, but probably fairly small because of the amount of mass that they've lost. But that does not mean that they are any older or younger than an Oort cloud comet. All of the comets we believe are about the same age, which is essentially the age of the solar system, 4.6 billion years old.
Thank you.
Yep. And so these smooth areas that are manifesting here on CG, somebody by the name of Bjorn Davidson, a colleague of mine from the Rosetta mission, actually simulated how much dust, like how thick that dust is, given the temperature of the different regions of the surface, the rotation rate of CG, and the shape model and everything, where there might be a few more shadows based on the curvature of the body and everything. And for various regions that you see here in this northern hemisphere area, you can see everything from, let's see, this is in thickness of meters. So everything from, a few tens of centimeters to 3.5 meters thick of this fallback material exist on CG, and potentially other comets who suffer from extreme seasons like this one. So if you want to go and you want to find that pristine material on a comet, this sort of informs us for future missions where we might have landers, diggers bringing home samples. Do you want to sample that material that's been processed and has fallen back on the comet? Or do you want to get to the newer, more pristine ices that were that original formational material from the beginning of the solar system? And that'll help you choose whether you go to a smooth area or a rougher area. And here's just another example of one of those smooth areas during the final descent of the Rosetta mission in 2016 in September. We got very close, and these are the two cameras that were carried on board, the wide angle camera on the left and the narrow angle camera on the right. And you can see just all of this material that's fallback material covering up boulders and such that are over here. You can probably make out that these little lumpy areas here looks like maybe a fresh snowfall over top of a boulder or some formation, here. You can just imagine that that's all this dusty material covering up a boulder that might be sitting there on the surface. Okay, so I've talked about the comets we've actually visited with spacecraft. Now I'm going to move on to other comets and other processes like fragmenting, for example. We do know of several comets that have been measured and seen to fragment, especially in Hubble Space Telescope data. Hubble is a workhorse for our fragmenting comet population. Because when we see this kind of activity, of course, everybody turns to Hubble and says, oh, I want to get it in a higher resolution. I want to see what's going on. And you can usually ask for some of the target of opportunity or direct or discretionary time in order to do something that you didn't plan a year ahead when they have their regular cyclic calls for observing. So here on the left is comet Schwarzmann-Bachmann 3, observed in 2006 to break up into many pieces. It is still an active comet that we observe and monitor every apparition. It still has a core nucleus that you can see in your observation. I mean, you can't see the nucleus, but you can know where the nucleus is. It's still a condensed body with a coma. But in these Hubble Space Telescope images, you can see all of this material that are actually like little tiny nuclei that broke off of the main nuclei that are then flowing down into the tail. We also saw with Hubble in 1994, when Hubble was brand new in space, it pointed to Shoemaker-Levy 9, which was a comet that was headed for Jupiter. Jupiter's gravitational pull was pulling it not just into Jupiter itself, and then you have no more comet, but it was also shredding the comet into pieces. It was pulling the comet apart. And so we actually got from those measurements, or the inclination that comets are not real solid bodies. Otherwise, it would not be able to be pulled apart quite so easily by Jupiter to disturb it into so many pieces. And here are the scars it left on the in the Jupiter atmosphere, and each of these scars is larger than the Earth in diameter, and so it took several months for those scars to clear up in the atmosphere of Jupiter. And you can just imagine, something like that happening at Earth. It's going to leave some destruction and scars here. All right, so moving on to some other comets that are well studied, but now I'm taking a jump from all these Jupiter family comets and the periodic comets to the comets that have come from the Oort cloud, and comets that are still well studied or bright enough to have had a significant observing campaign when they came around the sun. These comets it's the first time we've seen these comets in our generation because they have multiple 1,000-year orbits. They were perturbed, they came in, they've gone back out to the Oort cloud or the inner Oort cloud, and they're either never going to return again, or their periodicity is just several thousands of years long. And so two examples of those are HAL-BOP and Hyakutake, which were around in the mid-1990s. So in 1995, HAL-BOP was discovered at 7 astronomical units. An astronomical unit is the distance between the Earth and the Sun. So it was 7 of those away, which means it was between Jupiter and Saturn when it was discovered. This is great news. First of all, comets, as I mentioned, are small, dark objects, and it's very hard to detect them when they're far away. So it was already active when it was detected. We saw it because of its coma. And we discovered this comet that's not one that's been around the sun and processed around the sun with all this fallback material and maybe lost of some of its volatiles already, because we saw it for the first time out at 7 AU. So we're actually going to be able to watch it during that campaign come in and around the sun, not for its first time, but for a time where it's not doing it every 5 years. So there's a lot of information to be gained from seeing a comet during a full path of an apparition, where it's starting from where ice is still ice and hasn't sublimed, coming in around the sun and going back out.
Hey, Lori, I have a question.
Sure.
So when a comet's coming around, in the different publications and in the news, there's a lot of hype that this could be the best view ever and everything else. And like a weather report, many times it disappoints for those of us who love observing them or imaging them or both. And so could you explain where that prediction comes from in the first place and why it could be off so much?
Sure. Yeah. So comet of the century, right? That's like the famous grab line of news news outlets. So, and we've had several of those in the past couple of years where, oh, this is going to be the comet of the century and get all the hype. So when they're first discovered, sometimes it's just a moving target in the background star field. And that moving target may or may not have a coma. If it has a slight coma, which basically means it's not a point source, but it has a little bit more to it than the point spread function of your detector. And so if it has a coma, it's already active and you're like, okay, this is a comet, it's coming in, and you start making estimates of if it's at 7 AU, and I know what the insolation from the sun is at 7 AU just by, what's the black body temperature out at that distance. How active is this comet? How much water, CO2, dust, whatever it's producing at that time, depending on where it's discovered. You then have to extrapolate. Well, if it's doing it out at 7 AU, where it's only 100 Kelvin temperature, when it comes into 1 AU, it's going to be booming, right? It's going to be shedding all kinds of material. Those predictions are sometimes wrong because of the assumptions that go into that extrapolation. So things like the size, the size of the dust that you're measuring in the coma, the albedo, the reflectivity of that material can have orders of magnitude in your estimations. And so, we always go through and say, well, we always assume a comet is 3 or 4% reflective. That's its albedo. If something is slightly brighter or a little less, they're in the ballpark, that is generally true. But if you assume that and you've detected it, you can say, okay, well, this is approximately the size because I saw it at 7 AU and it didn't take me until 3 AU when it was twice as close to detect it. So you can say, well, maybe that nucleus is larger, or it has a fairly large coma, so it's already active. So surely when it gets close to the sun, it's going to be extremely active. Depending on how often it's come around, it may have exhausted some of its volatiles, meaning it used up all of the volatiles already. It lost them the last time it came around the sun and it's somewhat dormant. it could mean there's lots of things that go into that initial estimate, but that is oftentimes what happens. Sometimes they start fragmenting, and when they fragment, then they aren't as bright. You know, the fragmenting event might be a bright outburst, but then they still needed to wait 2 more AU to get close to us for them to be the naked eye comet, just because of the magnitudes.
Thank you. So Joseph asks a question here. He asks, when Earth flies through comet debris, meteor showers, do we ever try or have we ever seen or measured H2O or water particles falling through the atmosphere, kind of an atmospheric rainstorm?
That's a very good question. And actually, so we do, when we know that we're going to be going through a meteor shower or a comet tail, we do generally have some sort of observing campaign where we are looking for the dust particles as they come through the atmosphere. And of course, that's what the meteor shower is, right? It's the particles coming through the atmosphere. They're burning up due to the friction of the atmosphere, which is why we see the big streaks. Water would not survive that. If it's an ice particle that hits the top of the atmosphere, that moment the friction happens, it's going to sublimate into gas at the very top of the atmosphere. So the question of have we ever looked for ice in those tails or trails? They are very diffuse, and by diffuse I mean not very dense at all. So these particles are spaced quite far apart, even though they look, you know, in this picture, this tail looks like, you know, you're flying through a cloud, when in fact those particles would be, you know, more dispersed than the dust in the room around me right now. And so so detecting the dust as it comes through the atmosphere, and seeing the dust as it's reflected when you have a very long tail in the sky is one thing, but detecting water particles which would not make it through the atmosphere, so you wouldn't be able to measure it through the atmosphere. I think they're just too far between, you know, very low density in the tail itself to make that measurement. When we make the measurements, for example, I showed the ice on the surface of Temple 1. That ice is only 0.5% coverage of the surface, but it was a concentration of ice that needed to be measured. We're not going to have a clump that big or a concentration of ice that big to actually make a measurement of the ice in the tail at this point. Now, as we get, you know, more powerful telescopes like James Webb, we might be able to search out ice in tails, but at this point we just don't have the sensitivity to see the low density and low quantity of ice that might be there.
Thank you. Daniel has a question. He's asking, can we see the meteor shower here in Columbia tonight or this weekend, or do we need to be out in the country in darker skies?
I've seen meteor showers in College Park, which has bright lights. I've also seen them out in much more rural areas. And so you just get lucky and when you're looking up and how many meteors are expected per hour. So you should be able to see them in Columbia if it's a good show.
Thank you.
Okay, so any others for at the moment?
No, not at the moment.
Okay, fantastic. So the fact that we were able to study Comet Hale-Bopp as it came in and then receded from the sun, we were able to make, we call this the Christmas tree among all the cometary scientists, because it was a plot that was very colorful in its original publication, and it has sort of that shape of the Christmas tree. The activity turned on, it grew until we got to perihelion, which is this middle line, and then it decreased, something you would expect. The sun warms up the comet becomes more active, the comet starts going away from the sun, it becomes less active, things start recondensing, or the ice is just not sublimating any longer. And so we see that behavior almost symmetrically in every single one of the constituents in the comet. So we see it in water, we see it in the carbon monoxide, we see it in the carbon dioxide, we saw it in methanol, we saw it in HCN, all kinds of materials that we detected in Comet Hale-Bopp. So we expect that this was a similar behavior that just about any comet would follow. We've been surprised by several that do not have quite the symmetry, where the main volatiles, which are the main ices that are in a comet, are water, carbon monoxide, and carbon dioxide, and they aren't always as nicely symmetric. But this is the sort of the canonical Christmas tree and activity. If you're going to assume, like somebody was asking earlier about, oh, if you're predicting this comet of a century, it's going along many of these assumptions where it's going to peak at perihelion and it's going to go back down. That water will become the dominant thing when you get very close to the sun because it can finally melt or sublimate once it's inside 2 AU. But that does not always happen. Hyakutake was another comet that had limited studies because we only detected it a few months before its perihelion, not several years as we did for Hale-Bopp. Okay, so while I'm on the Oort cloud, I'll just mention another comet, Comet McNaught, which maybe other than Neowise, which we all had the opportunity to see during the first summer of COVID. Comet McNaught was a very bright comet that you could see in broad daylight as exhibited by these images right here from mainly the southern hemisphere. So we didn't get to enjoy Comet McNaught as much as our southern hemisphere friends, but had an extremely long tail, and all these striations in the tail made for great pictures and some really good studies. Okay, so I mentioned a few moments ago that water, carbon monoxide, and carbon dioxide are the primary volatiles within a comet, and that water is usually the most productive. It's the one we can most easily detect because of the detectors on Earth and in space around Earth. We can very easily look at water. We know what to look for. We can study OH, which is a byproduct of water once the sun's photons hit the water molecule. Whereas carbon dioxide and carbon monoxide are a little bit more difficult to detect. Carbon dioxide, you have to physically be outside of the Earth's atmosphere to detect, so we can't observe it from the ground like we can water. And carbon monoxide just has to be really, really bright and really abundant in order to observe it because the lines are fairly weak. So there's an unusual comet that came around in 2016 called C2016 R2 Pan-STARRS. And this one threw us for a loop because it was not water dominated, even when it was at its warmest part at perihelion. It was actually carbon monoxide dominated at 2.8 AU, which was near its perihelion distance. It had the larger chunk of the pie, right? More than 75% of its gaseous coma was made of carbon monoxide. And it also, over here on the left, this is just the structure in a spectrum of nitrogen gas. And so we saw nitrogen from the ground, from an observatory down in Texas. We saw this nitrogen signature very, very strong, which is also not very normal. And so we knew that combination of the nitrogen and the CO, that this is a very unique comet, or at least very different from the comets that we've studied in the past. It's not to say it's unique in the grand scheme of comet population, and surely we're going to find more like this in the future, but this was the first one we saw with such a stunning amount of carbon monoxide. So that leads us to, okay, if we detect comets that are further away from the sun, where water cannot be activated because it's just too cold, the ice will stay ice. It won't even change from an amorphous form in a phase change to a crystalline form. What is causing activity, and how would we have any hope of actually discovering a comet that's much further from the sun? And we can either hope for larger comets or more powerful telescopes, or comets that have more of this carbon monoxide and carbon dioxide material and composition that activate them much further from the sun. And so one example here is Comet C 2014 UN 271, Bernardelli-Bernstein. This comet was actually discovered in 2021, so last year, and it already had a coma. Now, the trick here is that at discovery, it was about 25 or 26 AU from the sun. So it was as distant as Uranus or further when it was discovered. So much further than any comet that we'd ever discovered. And we went back to, when I say we, I mean the cometary community in general. We went back to observations that are in all sky surveys, Catalina Sky Survey, for example, Pan-STARRS, various catalogs that are out there that just take images of the sky every night. And we actually found pre-covery, so pre-discovery observations as distant as 34 AU. So we could determine what its orbit was from the 2021 observations. We backtracked that to find out where we could first find it. And we just started looking in that quadrant of the sky for this comet. And we found it, like I said, out at 34 AU. It was point-like at that point. So it was a star-like point, but it was moving with its known velocity in the solar system, but it did not have a coma at that point. So by around 24 AU, so still beyond Saturn, we know that it has continuous activity and a coma. Here is an HST image of it at 19 AU. And you can really see the coma and the extent of the material coming off of it.
We have a question in the chat from
Sure.
Arjun.
Mhm.
Do comets and asteroids closer to the sun appear different in spectra? Would you have to account for more error factors than usual?
We would not have to account for more errors. When they're closer, they are brighter. So the spectra are actually more definitive of what you're seeing as far as the composition. Comets and asteroids look different spectrally. They have different spectral slopes, and asteroids, because they don't have a lot of volatiles on them, they don't have the coma that sets them apart from comets in general. There are a few main belt comets or active asteroids that we think might have some water on them, but it's very, very minor constituent compared to a comet. And so when you look at their spectra, if it's got emission lines, which are the positive lines, you're looking most likely at a comet with a gaseous coma. If you see absorption lines, you're probably looking at an asteroid with something absorbing on the surface. But the spectra of something further away doesn't, there's no more error in that as far as trying to determine what it is as far as the slope or determining whether it's a comet or an asteroid. You'll just have less signal further away. The magnitude will not be nearly as bright.
Thank you.
Okay, so looking at these observations, specifically from the HST observations, where again, the resolution is much better, you can sort of subtract the coma by taking an average of all the coma, subtracting that from the image, and you're left with the point-like source in the middle, which is presumably the signal from the nucleus itself. And again, you have to put in a few approximations as to the albedo, that reflectivity of the nucleus, and possibly the temperature or the size of the dust that formed the coma as you subtracted it off of your images. But the measurements, and it's come from some radio astronomers, it has come from the HST observations, and it came from a telescope in Hawaii as well. They have come down to within 10 kilometers. They believe the diameter of this comet, Bernardelli-Bernstein, is 130 kilometers. That is huge. That is 2 to 3 times the size of HAL-BOP. That is many tens of times Comet Halley. This is a huge comet, among the largest known. And its perihelion is not until 2031. It's already active. We've already discovered it. We are watching this comet, probably because its perihelion is not very close to the sun. It's not going to come anywhere near close to the Earth. The perihelion distance is 11 AU, so it's still beyond Saturn as its closest distance to the sun before it starts heading back out to the outer solar system. But the fact that we can already detect it, and the fact that we have instruments and telescopes like James Webb with the high spectral resolution and the high sensitivity, and other ground-based observatories like the Rubin Observatory such that are coming online over the next several years, we should be able to have a very good observational campaign of this comet, even at a distance of 11 AU. The water will never be activated, so we'll really get a feel for what other volatiles are on this comet. And that leads us to the final comet of the evening, the one that was in my abstract, which is C27K2 Pan-STARRS. And I left this one for the last comet because its perihelion is in December. Now, unfortunately for the Earth and all of us Earthlings, the viewing geometry is very poor from the Earth for perihelion. It was fine up until the end of October, and now it's sort of in a window where it's opposite of the sun, so we cannot look at it or observe it because we'd be staring at the sun. It would be a daytime object and too close for any of our telescopes to observe. And it's there until February. So it's in an avoidance zone for James Webb. It's in an avoidance zone for Hubble. The ground-based telescopes can't look at it. It's possible that SOHO or SWAN or Parker Solar Probe or something that's looking at the sun might get a glimpse of it at some point if it comes in the field of view, because they are allowed to look at the sun. But we from the Earth over the next couple of months are not going to actually be able to observe Pan-STARRS. So what's the history of Pan-STARRS and why was it exciting? Similar to Comet Bernoulli-Bernstein, it was discovered at 16 AU, so not quite as far, but still a pretty good distance. So we've been watching it for over 10 AU as it passes into the inner solar system. It was discovered in 2017. Again, we went back to pre-discovery observations and inferred that it had activity all the way out at 34 AU. So we saw it as far out as we did Bernstein-Bernoulli, but it was active, unlike BB, which we didn't see turn on really until 24 AU. This one's been active since 34 AU. So we're really trying to figure out what are all these processes that are happening on comets that make them so active at large distances, and why are we finally lucky enough that we're starting to detect them, whereas we've never been able to detect these before? It's really been in the past couple of years these things have started popping up. Is it just the sensitivity of all of our surveys, or is something else that we finally understand what we're looking for comets that were helping us discover them? Now, I'll mention it's not the first trip into the interplanetary region. It came around 3 million years ago. Now, the heat that it felt, the insulation from the sun it felt during that perihelion passage should have completely dissipated. It's not harboring any of that heat internally any longer. So whatever is happening for this current passage is because of its current passage and its current warming up from the sun. And as I mentioned, the perihelion is December 19th. You can see its coma growing over the past 4 years, from 2017 to 2018, 2019 to 2020. These are Hubble Space Telescope images with contours to help you see that it's not perfectly symmetric around the center condensation of the nucleus. And the activity is well outside the water snow line. So still at this point, it's beyond 2.5 AU, and that's where water generally turns on and is fairly active. But we have detected CO with this radio line right here, this bump with signal to noise of about 3 is a measurement of carbon monoxide at temperature of about 55 Kelvin, which is too cold for carbon dioxide to be active. And as I said, it's too cold for water to be active as a gas. However, we've also made this, this observation and detection of water ice. This absorption band right here is well known for ice, and this one right here is well known for ice, the fingerprint of ice if you see it in the coma. So there's ice in the coma and there's carbon monoxide. So now the question is a similar situation and process happening on K2 pan-stars, like it was on Comet Hartley 2, where you had this jet of CO, in this case, instead of CO2 there, pulling out a bunch of ice that was deep in the interior of the comet.
Dr. Figa, we have a
Yes.
couple questions in the chat. Ken would like to know, how do we know it came around however many million years ago?
3 million years ago, good question. So there are mathematicians and cometary scientists who actually study the orbits. Once you know where the orbit is in the sky, you can mathematically determine that elliptical orbit. And if you draw that orbit back in time and you include all the perturbations as it flew past Jupiter and, you know, the 3-body problem of this comet entering the inner solar system and going back out, seeing where it is, and you backtrack even where there might have been some stellar disturbances or gravity interactions, they can actually backtrack the most recent time it was in by the sun. And at this point, the determination, it was 3 million years ago. Now, depending on how close it gets to Jupiter or how close something gets to the Earth or how close something gets to the sun, you could have a perturbation that once that happens, it kind of erases the history and you can't make a very accurate backtrack at all. You might be able to say, oh, this is when it's going to come around the next time because I just saw how it perturbed it. And this is what's going to happen for the next millions of years. But if it didn't have any close encounters with Jupiter, or it didn't come in too close to the sun, or it wasn't in a very busy passing star field or something that was relatively close in the grand astronomical scheme and distance scales, then you can backtrack fairly accurately.
Well, thank you. And there's a second. I'm sorry. Were you
mathematical
not
game.
finished?
Yeah, no, I was just going to say it's a big mathematical game.
So Arjun would like to know, have ion tails and a higher level of ions on comets lead to unusual chemical reactions?
Do you mean within the tail itself?
Well,
Arjun, do you want to elaborate?
yep, yeah. So when I mean abnormal chemical reactions, it may be on the surface or within the tail, anywhere throughout the comet.
Yes, so that's a very good question. And yes, the solar interaction with comets is very extensive, and the ionic interaction as well. So there are chemical reactions. So when we look at the comet and the coma, and we're trying to understand, okay, that primordial material that was there 4 billion years ago, how processed is it? How accurate are we actually seeing that original material, or how different has it undergone lots of processes and chemistry? So the more pristine the ice, the more you can trace it back and have a little bit better confidence that it's original material. So that means something deeper from within the comet nucleus that's maybe being pulled out by one of these jets that are a high volatile jet like CO or CO2. And then you can look right in that very near coma, because that's the stuff as it's just come off of the surface or just come out of the comet, and it still is as pristine as it's going to get in nature. It's still preserving whatever it had as it sublimated. And so the atmosphere of a comet protects itself from some of the solar wind, just like the Earth's atmosphere protects us from the solar wind and the energetic particles. And so depending on how big the coma is at any given time, the solar wind only penetrates so far and only activates some chemistry in the outer coma. So if you're studying the outer coma and trying to say, oh, this is the chemistry I see, that must be what the comet is made out of, you're probably looking at things that are once, twice, 3 times over processed by other interactions with gases that are in the coma or with the solar interaction. It's the material very close to the nucleus that you can trust that probably has less interaction with the solar wind.
Very
Okay.
good. Are you good, Arjun?
Yeah, I'm good. That answers my
Okay.
question.
We have a question from Bob, and he'd like to know how often do passing stars perturb the Oort cloud?
Yep. Very good question. And pretty much every time we have an Oort cloud comet coming in, it's been perturbed by a passing star. So every couple of years, there is a dynamically new Oort cloud comet. And that's a figure from statistics. You know, we determine these orbits, trying to backtrack them again and saying, okay, did they come from the Oort cloud? Have they been into the inner solar system before? And if not, if mathematically we can say that's where they came from, a NEOWISE spacecraft is looking at all these small bodies, comets and asteroids, and looking at their orbits. And I think in 2016 or 2017, a paper came out that did that mathematical probability that looked at, okay, we've discovered X number of new Oort clouds over the past 4 or 5 years of NEOWISE's observing campaign. And based on that, how many would we see in any given year to help you both decide if you could send a spacecraft to them that might be on the shelf waiting for one to be discovered. And also just so people know how many do we really expect to be out in that Oort cloud population. So about every 2 years, we expect an Oort cloud comet to come in, and it's perturbed by something. That's how it gets in here. So presumably a passing star.
So how close would a passing star have to be?
That's a good question, and I'd have to ask a dynamicist, or you'd have to ask a dynamicist. I don't know what the distance is.
Great. So Arjun would like to know, would reactions in the outer coma of the comet compare to reactions on the early Earth, leading to eventual life on the comet?
Good question. So there are a lot of organics on the comet surface. We've actually seen with the Rosetta mission, we've found glycine, we've found phosphorus, we have found other organics and alcohols, things that are basically building blocks for life, building blocks of the amino acids, things that life as we know it have to have in order to be life. And so, yes, if you've got some kind of additional chemistry and that interaction with the solar wind happening, then there is always that potential that you've spurred something. With the number of comets out there, there's chemistry going on. I will not venture to say whether there's any kind of life on comets. We've not seen any. It's all just the basic building blocks of the amino acids that we've seen so far.
Very good. I think we're caught up.
Excellent. All right, so we've seen ice, we've seen CO. What's dragging water ice into the coma so we can detect it at such pretty good signal to noise, quite frankly, because you see right along here, everything is very nicely in line with this slope, which is typical of a comet. And then you see the data get a little bit noisier, but also fall into these two fingerprint spectral absorption features of water ice. So is it the same process as Hartley 2, or is it a different process because this is further away from the sun? It's being driven by CO, not CO2. Just is there something else going on? And these are studies that we are undergoing right now, and we'll have to do with other comets as well. So K2, as it's coming in, it's brightening, and this sort of goes toward what somebody asked earlier about, comet of the century. How do you make these predictions? Well, the red line is basically the prediction. So when the news outlets say, oh, it's going to get really bright, it's going to be naked eye, visible magnitude for naked eye is what, 4 or 5 magnitudes. This one was never predicted to be brighter than 8 magnitudes based on that red line. And right here before it left the good Earth observing geometry, it didn't even quite make it to not quite to the 8 magnitudes. It's like 9, maybe 8.5 magnitudes. That is from the visible magnitude. So that is taking into account the coma, the nucleus, everything in some aperture size that has been measured. What about the water production rate? And the water production has started out slowly at 3.5 AU to where it wasn't detected much earlier than that as far as the water. And then, you know, as it came in closer and closer and got to almost 2 AU, perihelion's at 1.8 AU, it's at 1.9 AU right now. The water production jumped up to 1 × 10⁹, which is fairly typical for an Oort cloud comet. The Jupiter family comets are usually around 1 × 10⁻28 molecules per second of production of water when it comes to perihelion. That's what Temple 1 and CG were. Hartley 2 was a little bit higher, but it was that hyperactive comet activity. And then HAL-BOP was at 1 × 10⁻29. So this is about on par with the activity from HAL-BOP at 2 AU at 1 × 10⁻29 molecules per second. Now, luckily for us, when it comes back into the Earth's observing geometry at 2 AU post perihelion, hopefully we'll be able to make those same measurements as it's receding from the sun, and we'll see if it's a symmetric comet, if something funny goes on and it just keeps releasing water. But we predict that it's going to sort of be this pyramid shape here. And I'm going to end with this image, which is Comet K2 Pan-STARRS at 1.9 AU. It's one of the last ground-based observations before it was no longer available to the general public and viewing. And I give credit to the person who posted it online. It's a beautiful picture. You can see the tail, you can see the nice coma, you can see the blue haze color of the coma. And so the future of cometary studies, these distant comets that are active, and the processes that are going on comets to make them active. Here's a plot just to show you. I liked from a paper I recently read, which basically they were putting into context Comet K2, which is over here. So the distant, or the x-axis is discovery year. So it was recently discovered in 2017. And the y-axis is heliocentric distance. So it was active and discovered at what distance? So K2 was active and discovered out at 16 or 17 AU. This comet C2010U3 was a little bit further away and discovered a little bit earlier. Here's where that K2 pre-covery at 34, well, this one actually was at 24 AU, but there was another one, as I said, at 34 AU where it was active and found in the pre-covery data. And just for kicks, way up here on this scale is that comet BB, right? That comet that's going to come into about the distance of Saturn, not quite, and go back out. So this comet is extremely far out when it was discovered in 2017. I'm sorry, in 2017 in the pre-covery observations, it would have been way up here. So with the higher resolution and sensitivity of things like James Webb and the other surveys that are coming online on the Earth, we're going to see a lot. We're going to start filling in this region of the cometary population. We're going to get a lot more of these active, bright comets that we can actually do some science on. And maybe the predictions will come true that we'll actually get a comet of the century over the next 10 or 20 years, because we'll know what to be looking for. And maybe they won't fizzle out before they get to us. And of course, the final note here, there are also interstellar comets for us to be looking for and to be excited about. They do exist. We've seen 2 interstellar bodies so far. The first one, Oumuamua, we believe was more asteroid-like. But Comet 2I Borisov was definitely a comet. We saw a coma, we saw cometary activity, we saw what we call perturbations to its orbit based on it having cometary activity and mass loss. And so we also saw this before its perihelion, whereas Oumuamua we saw as it was actually going out. We didn't catch it as it was coming in. So for Borisov, we saw it coming in and receding, although very quickly, because an interstellar comet has an extremely high velocity and usually does not come in along the ecliptic, but comes in at very high inclinations to the ecliptic. And so they are very hard to find and very quick as they zoom through the solar system and past the sun. But anyway, we've seen Borisov. We were able to look at it spectrally as well as with visible cameras. And it's very similar in so many ways to our solar system comets. And so the processes that we're learning about within our own solar system and our own comets so far probably can be extrapolated to some other solar systems, even though the solar system architecture that we're seeing with all these exoplanets is very different. The comet and that material might be very similar because Borisov was similar in composition and many other properties. So with that, I thank you very much for having me, and I'll address any other questions you might have had.
Hey, that was awesome. Hey, Joel, I saw you had a question.
Joel?
Oh, yeah, I can, excuse me. In your abstract and bio, you mentioned hopefully leading a small satellite mission. Could you elaborate on your vision?
Yes, so I have been working with Lockheed Martin over the past several years on multiple projects, but one of the projects, they actually came to me and asked me if I would like to be the PI, which is the principal investigator or the lead of a small satellite mission. And so NASA puts out a call every couple of years for these small shoebox size satellite launches and flight missions. And it can be any science that you want it to be, but it has something like a $50 million cost cap, or that's historically what it is. The new planetary decadal just came out, and it's unclear how the simplex and small satellite calls are what they're going to do exactly in the future for NASA. But we're hoping that they're still going to have such a mission, which is smaller than their Discovery class, Frontier class, and large missions like Galileo and Cassini. So anyway, this small satellite would be something that has miniaturized instrumentation, which is sort of the new technology, right? You've got small cell phone type of cameras. You have maybe some little experiment that you're going to do. People have been working and fabricating small spectrometers that are accurate enough to do some sort of experiment or measurement in space. And so you put a package together in this shoebox spacecraft. It gets a ride share, which is one of the downsides. You don't get to pick the launch date. So you have to maybe be somewhat agnostic in your target or your orbit. If you're riding along, for example, like all the Artemis tag-alongs that were just launched. A lot of those were the CubeSats of a similar kind of formulation, but they were all at least going to the moon. A lot of the simplex or these small satellites hitch a ride with Psyche, hitch a ride with Lucy, hitch a ride with Dragonfly, they hitch a ride with some other planetary mission. So they start off with whatever that delta V and that intended orbit is for that spacecraft, and then they can go elsewhere depending on what propellant and stuff that carries with it. So the spacecraft that I'm interested in is going to go to a comet. It's unclear which comet at this point because it depends on the call of the actual NASA proposal. But we're going to try to look at a fragmented comet, or we're going to look at one of these interstellar comets if one happens to be discovered and we can build to it quickly enough, or one of these Oort cloud comets. We're trying to get away from Jupiter family comets, because not that we know them like the back of our hand, but that is where we have 5 examples, right? We don't have an example of an Oort cloud comet yet in any of our flybys. Clearly, we don't have an example of an interstellar comet in any of our flybys. And so the small mission would be, it's allowed to have higher risk because it's a smaller loss budgetarily, And so you can do something a little bit more riskier. You don't want to fly a very complex, large, expensive spacecraft past a fragmenting comet. They are very unpredictable. You would have space debris, comet debris that you would be interacting with. But a shoebox size, it's maybe a little less expensive. You'd be willing to do some maneuvers near a comet like that. So those are the kinds of experiments we're thinking about, and to be determined. Hopefully NASA will put out a call, Congress will approve money for such a line item for NASA, and I'll be moving ahead with a collaboration.
That's
Wow,
exciting.
congratulations on
Good.
that.
Good luck with that.
Thank you.
There is another question in the chat. Robert wants to know, why might C 2016 R2 have so much more CO than other comets?
That's a very good question, and we're all pondering that. We do not know. No, in all honesty, we do not know. It could have been formed in a different region of the solar system where only the CO was condensing and the other volatiles were not. So further out in a very, a much colder region where the CO could condense, and so it stuck to the grains more readily and formed the comet. We're not really sure, because all the other comets we've seen so far have a much better mixture or are water dominated. But this is, I think, just the tip of the iceberg. I think we're going to start seeing a lot more comets, especially with James Webb, which can see CO2 and CO simultaneously with measurements of water. So we're going to see other comets that have higher volatility compositions.
Thank you.
Well, thank you very much, everybody. That was awesome.
Awesome.
So thank you very much. I always say you can always tell how much the group enjoyed the presentation by the number of questions and the quality, and I think they passed, and that, so, or you passed. But we really appreciate it. Hopefully you'll be able to stay for the rest of the meeting. We've got some cool stuff to talk about and some pictures to show that you might enjoy.
Sure.
And again, if anybody has any questions, pop them in the chat, and just so we don't forget. And then when we get through the rest of the program, we can get back to those if everybody has time. So I'm going to share my screen again and remind everybody that if you have a suggestion for our guest presenter, guest speaker, it's right on our website. You can see suggest a speaker and pop your information in there, and then you don't have to contact them. I could contact them, or one of the members of the board will contact them, and we're always looking for very good speakers like today. I want to let everybody know that in December there won't be a speaker, as we have our annual holiday party, which we'll talk about here in a second. But I do want to let you know that in January, Lori had mentioned the DART program at some point in her presentation today. And in January, our guest presenter is going to be Dr. Nancy Chabot, depending on, I don't know exactly how to pronounce her name.
Chabot, Nancy Chabot.
From APL, and she's a planetary scientist, but she's the coordinator of the DART program. So we're very excited that she'll be speaking with us come January. And that contact came from one of our members, Phil Rogowski from STEM. So we'll be looking forward to that. So the next part here I want to talk about, I forgot to put a slide in, but so for the holiday parties, we always did them at Robinson Nature Center on the third Thursday of December. And we had to stop doing that during COVID. So now here we are, and the board has been kicking around some ideas, and I'd like to get your impact. So your impact. That was a comment slip, but get your input on this. So here's some options. One is we could go back to Robinson Nature Center, so I'm going to have to contact them right away and do our potluck and little celebration that we do, that we've done in the past. Another suggestion we had is that we do something outside at the observatory at Alpha Ridge, regardless of the weather. It could be cold, we'll just dress warm, and if it's nice, you could bring your telescopes. If it's not so nice, you could just bring your hot food, and we could turn on the power and, for inside and outside the observatory. So those are some ideas, and I really, and myself and the other board members would like your input, because we're gonna make a decision real quick. So what are your thoughts? Anybody? Just unmute and pop up. Wow.
Go ahead.
Hey, Phil,
Yes.
when we were at Alpha Ridge for the public party last week, the water fountains were all turned off. I don't know if that's a county thing. I don't know if we can turn that on, but that's a concern I would have for having the party there.
Okay, thank you. Yeah, we're not gonna be able to adjust whether the water comes on or off. That is, Parks handles that.
But
Okay.
the bathrooms would be open.
The bathrooms will be open. Right. Anybody else have any thoughts?
If we're voting, I'd go for the observatory.
Okay. Thanks.
I like indoor. I agree with Joseph.
Okay.
Daniel has his hand up.
Yeah, Daniel, jump right in.
I also vote would vote we do it at the Robinson Nature Center. And then I like how one year Joel Goodman did a planetarium show about how the Star of Bethlehem came out. So I vote do it and then play the planetarium show on how the Star of Bethlehem came to be.
Yeah. Actually, Joel, that's a good suggestion, Daniel. Joel will have to dial in because he's enjoying the island life until May.
But
So
I would be willing to give a shortened version or whatever version of presentation by Zoom, if you'd like.
okay. Daniel, great suggestion.
Could we do something in the planetarium? Could we have a special HAL planetarium event?
That would need to coordinate with Ellen Reinke at the center.
Maybe we could send out a poll to the membership, some kind of a survey, email survey or something.
Well,
and get a
good idea, except we're kind of out of time for putting all that together and everything. So we're gonna get the input from here. And that's a good suggestion though, Victor. So if we end up back at the Robinson Nature Center, we'll see if we could coordinate something with the planetarium. Yeah, because we're gonna have to give the Robinson Nature Center folks some notice. I would say that we're probably already late in giving them notice, so they're gonna have to, adjust schedules or make schedules. So that's why I'm asking these questions now, so I can pretty much get back to them tomorrow. Or get to them if that's what we decide to do. But I don't hear a lot of waving of hands and jumping up and down for doing something outside. So
Right.
sounds like we're going to default into towards the Robinson Nature Center and put together a program, and we'll get the potluck thing going, and we'll coordinate with for the planetarium and what time we'd start and everything else. So that's what we're going to do.
Phil,
Yeah.
one year we did an equipment exchange in conjunction with the
Yeah, that we did that during my first year, I think it was, the last time we were at Robinson Nature Center before COVID. Yeah, we did a holiday swap, or if somebody wanted to coordinate a sale with somebody, that you bring in your accessories or your telescopes, whatever you want to change off for the holiday season there with others, and it was pretty successful. So that's another good idea.
Do we have a consideration of number of people that that Robinson could accommodate there comfortably, especially in these COVID conscious days?
So I'll ask Ken. I could tell you that even during our best times, we never had really an overflow crowd. It was usually about, I would say, Joel, right? Anybody else was there, around 40 people, somewhere in there.
At the max for the holiday event, 40. Yeah.
So
that's plenty of room that's plenty of room in that auditorium.
Yeah. And even though the club has grown by well more than 100 people since our last time, but our activities have been kind of stable. as far as the number of people that show up, regardless whether it's a star party, one of these meetings. So so there's no reason to, we don't have any statistics that show that our participation at any particular event is greater than or by significant numbers. So I don't think that's gonna be an issue.
Okay, good.
Thanks, good point. Anybody else? All right, so I'm gonna move on. Thank you for your input. Get back over here. So so our webmaster, Ken.
Why don't we save me for next month?
Okay,
Because
okay.
you've
so
got all
Ken,
the images and other stuff to go over.
is there anything you want to highlight though, or talk about real quick with the website?
No, just, no, not tonight. I'll
Okay.
just save it for next time.
Okay, great, thank you. And Hannah's our social media publicity person. And Hannah, you have anything to, whether it's for Instagram?
So many wonderful graphic designs for this role. I don't know how I got so lucky. Thank you, Phil.
You're welcome.
I get to live out my Star Trek dreams, which is coincidentally, I also named my car the Enterprise. So I digress though. No, just a reminder, continue submitting to the HAL Instagram. You can find the submission link on the website. Thank you, Ken, for continuing to keep that up there, as well as Hoko Astro is HAL's Instagram page. You might even get promoted by some other fun accounts. The submitters, everyone who submitted for the October Object of the Month was featured on the Instagram of the Maryland Science Center yesterday, which was really cool to see. So yeah, just continue submitting. Love, posting anything that you might have, pictures of your setup, your data, final pictures, sketches, drawings, wide field, deep sky, planetary, videos, just really anything, this doesn't exist in a void, and it all definitely means something personal and different to each and every one of us. And that's really important to share. So yeah, there's my spiel. Thank you.
Thank you very much. So even though that we are coming to the end of our planned schedule events, I want to let everybody know that the observatory is working great, thanks to Victor and Hannah and Richard and others who have put a lot of time in. And so, as long as we continue to open for our impromptu star parties, if you're not getting those emails for impromptus, go onto the website, go into your account and, click on the thing that says you want to be on that distribution list. We want to use the observatory. So, Victor, you have anything you want to add to that?
Oh, it's all working.
Okay. Awesome. So it's time to move on to
Victor, has the observatory been winterized yet?
No, because we're planning on, winterization, I think, is what we do when we think it's going to be kind of put away and not used for a while. And I'm planning on going there soon just to do a couple of minor things, minor upgrades.
Yeah, it's things like turning off the dehumidifier and unplugging it and that kind of stuff.
Yeah, that's been done.
Oh, okay. Thanks.
All right, time to move on to our Astroimages, sketches, and some other stuff. So pretty cool from our own family here. So Gene, I know you're on. Gene, you want to describe what's about to happen here, Gene?
So I took pictures every, 15 seconds of the eclipse, and it worked out pretty good until it got to total, and then it hit the trees, but still it looks okay.
Pretty darn cool.
And that was the trees.
It was good. That's awesome. Want to see it again? Here we go. No extra charge.
Yeah, it does a little bit of funky brightening at the end there because I was upping the exposure time.
Very cool. So I kind of put these images in some kind of I try to always to put them in some groupings that makes kind of sense. So you can see a lot of hang on. There you go. Here's Richard. I know, Richard, you're on. See you.
Yeah, I'm on. This is just when I was sighting over my neighbor's house. It was about 6 o'clock in the morning and during total. And I labeled all of the big stars. It was in Aries around it and also Uranus. You can see it up here.
That was really cool. Really nice. Arjun, our budding imager, as well as educator for the rest of us. Go ahead and unmute. There you go.
Okay, so this is not the best image. This is like my first image with the new Astro equipment I got. I recently bought the Ioptron Gem 28 and it arrived like last week or the week before last week. But I just took a few pictures of the moon, stacked them, and tried to create some sort of HDR composition. So I think it turned out okay. So yeah, this is the result which I got.
Arjun, every time you do something, it gets better and better, and you just keep doing it.
Thank you.
And then Jim has got something a little bit different to talk about. Jim, you're on, right?
Yep. Can you hear me okay?
Yes.
Okay. So some folks know from presentations in the past, I do a lot of radio observation, radio astronomy, and one of my longtime topics now is meteor observation using TV signals. Let the meteor, when it comes to the atmosphere, it leaves an ionized trail behind. And the TV station I've been using since May to observe is out of Sault Ste. Marie in Ontario, Canada. And in October, this is the first time that I've ever seen a correlation between a visual observation of a meteor and a radio trace of what we're going to see in a second. So this screenshot here is a picture from a guy. His name is Ryan, and he's in North Royalton, Ohio, which is just south of Cleveland. And that event number, you can look on the IMO, International Meteor Organization webpage, and look at that event number. And he says he was facing from his property 30 degrees at 4:52 in the morning and saw this fireball for 3 seconds. And so I record the TV station every 8 minutes or 9 minutes. It takes a recording. And on the next slide, I mapped out the path profile from us here in Maryland to the TV transmitter there in Sault Ste. Marie is the path that I received. It's 640 miles distant. And the observer was this guy, Ryan, here in Ohio. So in that arrow is that's about 30 degrees. He's looking over the lake there. He's looking up into Michigan, stuff like that. That's about the direction. On the next slide is my observation at my house here in Anne Arundel County of the TV station out of Canada. And that's at the same time, 4:52 in the morning, in about 30 seconds, where that red arrow starts right there. And that trace is one of the largest I think I've ever seen. It's about 7 minutes in duration. So what Ryan in Ohio saw for 3 seconds, visually, I see for 7 minutes. That black line in the middle is the reflection of the TV signal coming down from that transmitter in Canada. And Phil, on the next page, on the next slide, I show, this is for those that are familiar or know what a spectrum analyzer is. So this is a TV signal. This is what a TV signal looks like in the radio world. And the arrow that I have pointing to the video carrier, that's basically what I'm waiting for to show up. It's a very, very, very narrow signal, very powerful, the most powerful part of a TV signal. And that's what that black trace was on the previous slide. So this is a general picture. This isn't like anything that's coming in from Canada. This is just a general picture. But the coolest part is, for all this time of doing this, that's the first time I've seen somebody correlated and in the right area of the country. Where, he's in Ohio and I'm picking up signals from Canada, and time coincident fireball that finally showed a trace. It was just, I was stoked to actually see it. And just for the folks that were talking about the meteor shower earlier, the same trace, it records 24 hours a day. I'm starting to see a lot longer traces with this meteor shower. Not as long as 7 minutes, but I'm seeing upwards of 2 to 3 minutes. And I'll definitely be checking Friday into Saturday morning and see what happens. So that's it, Phil. Thanks.
That's awesome. Anybody have any questions for Jim? Great, Jim. Thank you. James, are you on? James is not on, but James has once again given us some spectacular images to enjoy. And here's one of Ganymede that he took on November 10th, the one on the right. See that right there? And there was a lot of traffic on email back and forth when he first posted this. Then here's a shot he did of Mars, which you can see I got that in there twice. And then Bob, are you on? Bob did a sketch of Mars, and it's right around at the same time, and you see the similarities. It's a very nice job from Bob. And then Richard, this is one of my, for those of you who know, Richard's been sketching for many years and sharing his sketches with us. This is not a photograph. This is a sketch and the Flaming Horsehead Nebula, and I'll let him talk about it, but I love this one.
Oh, well, thank you. This is a drawing that I did just a couple weeks ago, and did it with a 6-inch refractor with a 67 millimeter eyepiece, which gave me 2.5 degree field of view with a image enhancer and a hydrogen alpha filter, 6 nanometers. And this is the horse head, which the bright star is the easternmost star in Orion's belt. And you have the Flame Nebula to the right of it, and the Horsehead Nebula, which is the dark nebula in the whitish patch to the below it.
That's great. I love the way of that nebulosity showing there.
The image enhancer really helps.
Yeah. Mr. Gene, another great one.
Yes, this is the Soul Nebula, which is half of the Heart and Soul Nebula. And I don't know, it's with a narrow band through an 8-inch reflector.
There we go. Very nice. Here you go.
And there's my last one. This is the Helix Nebula from when I was at the Staunton River Star Party. And I'd taken a picture of this before, and I could just barely see that top outer part. But this is with a new camera, and it showed way more of the outer stuff. It turns out a lot of these planetary nebula have dim outer extensions, and so it's fun to try and get them.
So why'd you choose that camera as opposed to any other one, the QHY?
Well, there's basically that one or the ZWO, and they use the same chip, so you just have to pick a company. But
Yeah.
this is, one of it's not the full frame, so this is a half frame camera. So, it's like as much as I wanted to spend.
Got it.
But it's very high QA, quantum efficiency, and it's a big chip, and so lots of nice things about it.
Very nice. That's a great shot. Chris, are you on? So Chris has been doing some experimenting, and he was showing this as using different types of processing. So he's still working on this one, and he just wanted to kind of highlight this. Usually he sent an email, he sent over to me. And then here from the Joe, are you on? Joe? So this is the that EV system, which is really cool. It's the same one that Grace has. I think it's a little different model, but it's that little 3-inch telescope that's just a live stacking imaging device. And here's a cigar galaxy that Joe took with the telescope, and then here's a shot of Mars he took with it too. Pretty amazing for a 3-inch telescope.
Looks like the moon for being Mars.
I'm sorry, the moon. They both start with M.
Yeah, and they're 4-inch actually, the EV
That's
scopes.
orange, okay.
Yeah.
Well, that makes a difference.
Yeah.
We're both red.
And that's it. So there you go. So I want to thank everybody for joining tonight. We are right on time tonight too. How's that? So it's been a great meeting. I'll get the information out on the holiday event and look forward to seeing everybody live and in person from the shoulders down. And if you are interested in being nominated or nominating yourself for a position for 2023, please send your email to Jim. Jim sent out a very nice email today. Take a look at it. That talks about the elections and the election process. And I could tell you, this is my third and final term as president. And I'll say more in January, but it is a great honor and a pleasure to lead this group because of all of you and the others who couldn't make the meeting tonight. So with that said, I'd like to wish everybody clear skies, and I'll talk with you soon.
Bye.
Have a good night.
Thank you, Phil. Thanks to our speaker.
Bye.
Great meeting.
Bye-bye. Thanks.